I want to start this lecture by summarizing the formulas we have seen last time. Precisely, if nabla tilde is the Levi-Civita connection for M tilde, and nabla is the Levi-Civita connection for M, then we have that nabla tilde y in the direction of x splits this way, and the orthogonal component is what we call second fundamental form. We have seen that the Gauss formula says that the tangential component, this one, coincide with nabla yx. We have proved the Gauss formula along a curve, which says how the covariant derivative of a vector field along a curve splits. Then we introduced the Weingarten map, considering first the normal component of the second fundamental form, and then defining an operator, a map, a linear map, Wnx, writing this way, and we proved the Weingarten equation, which says that Wnx changed after a change of sign is equal to the tangential component of this covariant derivative. Then we have seen the Gauss equation, which says how the Riemann tensor splits. This is equal to the Riemann tensor of M evaluated at Wx, y, z plus two terms which are more complicated. Then we introduced the normal connection, writing this way. Observe that we already considered this covariant derivative here, where we took the tangential part to define to improve that it is a Wnx change of sign. Instead, here we are taking the orthogonal part, and it's possible to prove that this is compatible with the metric G tilde of M tilde. Now I want to present the last of the fundamental equations for some manifolds, known as Codazzi equation. And in order to do this, I have to introduce a new connection. So suppose that this is a bundle satisfying this property. The fiber at each point P of M is the set of bilinear maps from TPM times TPM into NPM. You can prove as an exercise that this is a smooth vector bundle over M, and the smooth sections of F correspond to smooth maps from P of M times itself and values in sections of the normal bundle, and they are bilinear over psi infinity M, C infinity M. So now we can define a connection denoted nabla F, writing this formula, where B is a smooth section of F. Now I will use this new connection for writing down the Codazzi equation. It says that Rm tilde W x y orthogonal, this is equal to nabla f W second x y minus nabla f x 2 W y. I will not prove this formula, I just tell you the idea of the proof. Essentially, since here you have the orthogonal part of Rm tilde Wxy, the idea is that you take the inner product of left hand side and right hand side with n, where n is an arbitrary smooth normal vector field along the manifold, the submanifold M. So precisely, sorry for the typo, this is R, excuse me. So we have R tilde Wx y, this must be equal to nabla Wf 2 xy minus nabla fx2 w y multiplied by n. And the proof begins by writing down a formula for the left hand side. So precisely you have to expand Rn tilde Wx y n, which is this, and applying the Gauss formula, and doing this, while doing this you have to take into consideration only normal components. Sorry, I made another serious typo. Excuse me, today I made too many typos. So this is multiplied by n. I'm so sorry for the So I was saying that you have to expand this and use the Gauss formula. You have to take into account only normal components, because here you have the normal components of this vector field and also this one. Now let's change topic and let's try to find what is the geometric interpretation of the second fundamental form 2. In order to do this, we have to introduce the curvature of a curve. So suppose that gamma is a smooth unit speed curve in the submanifold M. Then we can define the geodesic curvature of gamma this way, k of t. This is the length of this covariant derivative along gamma. If the curve gamma is not a unit speed curve, then we have to find a unit speed reparametrization, and then we have to define the curvature So the curvature in this case will be the curvature maybe I should write at t. Now suppose that this is a submanifold of M tilde G tilde. Then we have two geodesic curvatures we have K. This is the intrinsic curvature of gamma as a curve in M, and we have K tilde, which is the extrinsic curvature of gamma as a curve in M tilde. So what is the relationship between K and K tilde? So suppose that P is a point of M, V is a vector in TPM, then we have that 2, the second fundamental form evaluated at VD is the G tilde acceleration of the G geodesic gamma V, and the second statement if V has length 1, then the length of 2 evaluated at VV is the G tilde curvature of gamma V at P. The proof of these two statements follows from a simple formula. Precisely, suppose that gamma is a curve satisfying gamma 0 equal P, gamma 0 prime equal V. Then if we use the Gauss formula along a curve, that is d tilde tx equal dtx plus 2 gamma prime x, where x is a vector field along a curve gamma. With x equal gamma prime, we get d tilde t gamma prime equal dt gamma prime plus 2 gamma prime gamma prime. Now if gamma is a G geodesic, that is gamma equal gamma V, then this is 0, and we get d tilde t gamma prime equal 2 gamma prime gamma prime. So now it is clear that if we look at this formula at 0, where gamma prime 0 is V, we get that dt tilde gamma prime at 0, this is 2 VV, which says that the G acceleration of gamma is exactly 2 VV. This was statement A. And if V is a unit length vector, which means that the curve is parameterized by arc length and its speed is equal to 1, then we have that k tilde is exactly to this. So this is the definition. Sorry, I should write 0. and this by this formula is equal to the length of 2VV. So this was statement B. So clearly K is in general different from K tilde. So this means that a G tilde geodesic that starts tangent to some manifold M in general does not stay in M. So for example, if you have a circle in R2, you can consider a geodesic of R2 which is tangent to the circle, and clearly this curve does not belong to M, which is in this case S1. There are some manifold where instead it happens that G tilde geodesic, which start at tangent to a submanifold, stay in that submanifold at least for a small interval. So I give this definition: a Riemannian submanifold Mg of M tilde G tilde is totally geodesic if every G tilde geodesic that it is tangent to M at t equal t0, stays in M for all t in t0 minus epsilon, t0 plus epsilon, with epsilon positive. What I want to prove is the following proposition. Which says that the following statements are equivalent. M is totally geodesic. In M tilde. This is equivalent to B, that is every G geodesic in M is also G tilde geodesic in M tilde, and this is equivalent to the fact that the second fundamental form of M vanishes identically. So we will prove that A implies B, B implies C, and C implies A. How to prove that that A implies B? So suppose that gamma is a geodesic of M. I have to prove that if M is totally geodesic, then this curve is a G tilde geodesic. For each T0 in I, let gamma tilde be the G tilde geodesic with gamma tilde T0 equal gamma T0, gamma tilde prime T0 equal gamma T0, gamma prime T0. So by hypothesis, there exists a subinterval I0 containing T0 such that gamma tilde T belongs to M with for any T in I0 So this is true because M is totally geodesic. Then I can use the Gauss formula, which says that d tilde T of gamma tilde prime is dt gamma tilde prime plus 2 gamma tilde prime gamma tilde prime. Now this is 0 because gamma tilde is a G tilde geodesic, and now we observe that this is a tangent to M, and this is normal to M. So if the sum of these two vectors is 0, then this means that each of these vectors must be 0. In particular, this is 0, which means that gamma tilde is a G geodesic on I0. But we can use the uniqueness properties of geodesics. So we have that gamma is equal to gamma tilde on I0 implies gamma is a G tilde geodesic. This argument can be repeated, can be used for any T0 in I, and this means that gamma is a geodesic, is a G tilde geodesic on I. So repeat the process for any T0 in I, and this proves that gamma is a G tilde geodesic because it coincides with a G tilde geodesic. So now I have to prove that B implies C. So B is the statement according to which every G geodesic in M is a G tilde geodesic. I have to prove that the second fundamental form of M is equal to 0. So as before, we fix a point and a vector, and we consider gamma equal gamma V, that is the geodesic starting at P with initial velocity vector equal to V. By hypothesis, we have that both these covariant derivatives are 0. So Gauss formula along gamma implies that 2 gamma prime is 0. In particular, this is true at t equal to 0, where gamma prime is a V. So I have 2v equal to 0, but V is arbitrary. So we can use a lemma which says the following. if I have two symmetric bilinear maps defined on V times V, where V is a space equipped with inner product, and this is a vector space, then if BVV is equal to B prime VV for any unit vector V in V, then they coincide. So we can apply this lemma with B equal to 2 and B prime equal to the zero map. So this says that 2 is identical to 0. Now we have to prove that C implies A. So we have to prove that from this identity implies M totally geodesic in M tilde. So let gamma tilde G tilde geodesic such that gamma tilde T0 is a point of M and gamma tilde prime T0 belongs to Tm. Take another curve, precisely a G geodesic, with the same initial condition, then we use again Gauss formula, and we get that T tilde T gamma prime is equal to dt gamma prime this is true because of our hypothesis. And this says that gamma is a G tilde geodesic. Now we use the uniqueness of geodesics, and we have that gamma is equal to gamma tilde on the intersection of their domains, So this implies that gamma tilde t belongs to M for every t in a neighborhood of t0. And this is exactly what M totally geodesic in M tilde means. And this is the end of the proof. What I want to do now is to present briefly what happens if we consider the following special case, where M is an hypersurface of M tilde. Hypersurface means submanifold of codimension equal 1. So this means that the difference of the dimension of M tilde and the dimension of M is exactly 1. Okay, so let's start from the definition of a special second fundamental form which is the one you studied in the course Introduction to Differential Geometry, and which is known as scalar second fundamental form. So this is the symmetric covariant to tensor field H define writing H equal to N. So in other terms, we take the normal part of the second fundamental form, that is H, X, Y. This is the inner product of N with 2 X, Y. We know that according to the Gauss formula, this one is the difference between this covariant derivative and this one. And we use the fact that if n is normal to m, then n is orthogonal to this, because this is tangent to m. Consequently, h of x, y, it is also equal to this inner product. Another consequence of this formula is that if n is a unit normal vector, then from here we get 2xy equal hxy n. Why? Because this is normal to m, and this is normal to m. We defined the Weingarten map for some manifolds. In the special case of hypersurfaces, we write S instead of Wn, and we call this the shape operator of M, and clearly we have the following identity: Sxy, this is equal to Hxy, and since H is symmetric, this implies that S is a self-adjoint endomorphism of Tm, and this means that Sx y, this is equal to x s y. Of course, you know that for an hypersurface we have two choices for the unit normal vector field. So essentially you can work with n or minus n. If you change the sign of the vector field you are considering, of course h changes sign. Now I want to write down the fundamental equations for a hypersurface. they are consequences of the fundamental equations for a submanifold. So we have Gauss formula for a hypersurface. This is immediate. Then we have the Gauss formula for a curve in a hypersurface. Sorry, H. Also, this one is immediate, because remember, this is the second fundamental form. We already observed a few minutes ago that the second fundamental form can be written as the scalar's fundamental form times n. Then we have the Weingarten equation, which says this. Then we have Gauss equation, and the Codazzi equation. Please observe that in this formula you need the last entry to be n. Let me check how much time I have. Okay, so the last, maybe the last thing I will do today is the introduction of the notion of principal curvatures, Gauss curvature, and mean curvature. So now we give a deeper look at the shape operator S. In order to do this, I need to use this proposition. Probably you already have seen this proposition in some algebra course. Which says the following thing. If V is a space with inner product and of finite dimension, and we have a self-adjoint linear endomorphism, the shape operator I introduced a few minutes ago satisfies this hypothesis with V equal TPM we have then V has orthonormal so V has an orthonormal basis of S eigenvectors and all the eigenvalues are real. I don't prove this proposition because I am interested only in its consequences. So I will apply this proposition to the shape operator S so according to this proposition we have that there exists an orthonormal basis of V of TPM B1, B2, Bn the corresponding eigenvalues are real. And this means that S Bi is Ki Bi. Of course, here I'm not using the Einstein convention. And what about H? If VW are in TPM and V is sum of VI BI, W is sum of WI PI, what is H of VW? You can maybe so remember that S, X, Y, this is H, X, Y. So if you know that this is true, then from that formula you can find easily that H VW is K1 V1 W1 plus K2 V2 W2 plus Kn Vn Wn. So the eigenvalues Ki are known as principal curvatures. The corresponding eigenvectors they're known as principal directions and we can define the Gauss curvature as the determinant of the matrix representing S, and if we use the principal curvatures, it's immediate to say that this is K1 times K2 times Kn. We have also the mean curvature, H equal 1 over n trace of the matrix representing S, or alternatively 1 over n trace with respect to G of fundamental form H. And it is clear that this is also K1 plus K2 plus Kn divided by n. Remember that in the definition of S, we made a choice for the unit normal vector field n. If we change n into minus n, then h becomes minus h, because the sign of all the principal curvature change, Instead, the sign of k changes only if the dimension is an odd number. So k becomes minus 1 power n times k. Let me check how much time I have. Okay, approximately 10 minutes. Okay, in the last 10 minutes, I will let me think. I will present the way we carried out the computations of shape operator for a surface in the Euclidean space. You know that the computations are simplest if the hypersurface is presented in terms of a local parameterization. So suppose that M is an hypersurface of Rn plus 1, and X is a smooth local parameterization of M. The coordinates U1, U2, UN on U gives give local coordinates on M. So let's observe that this tangent vector is pushed forward by the differential of x, and we can think of xu equal x1u xn plus 1 mu as a vector valued function of u, and you have this identity. And in the sequel, we use this notation, xi equal delta I x. So what we did so far is that we have the vectors which are tangent to the manifold, to the submanifold. Now we have to find n. So how to construct a unit normal vector field to the submanifold? Choose such that it is not contained in span of x1, x2, xn, then you can apply the Gram-Schmidt algorithm. To get E1, E2, En plus 1, this is an orthonormal. Sorry, I omitted to write that you apply this algorithm to x1, x2, x3, xn, delta over delta x j0. So you get this way an adapted orthonormal frame. The reason why this is orthonormal is clear. The reason why it's adapted is that the first n vectors are tangent to the surface because they are obtained by x1, x2, xn, which are tangent to the surface by construction. We have then two choices for the unit normal vector fields. You can choose n to be En plus 1 or minus En plus 1. So what I would like to show is that this proposition holds true suppose that M is an embedded hypersurface. Suppose that X is a smooth local parametrization. Suppose that x1, x2, xn is a local frame for Tm determined by x, as we have seen before, and n is a unit normal field on M. Then we have the following formula: Hxi xj. This is the inner product of the second derivative of x with respect to ui and uj, inner product, and I think it's better to prove this result next time. Thank you for your attention.